Alright, in this video we're going to be making a formula sheet for AP Pre-Calculus, and you're not allowed a formula sheet on the AP exam, but I still think it's a good idea to make one so you can have them all in one place, and it's a good thing to do as you're reviewing. So, let's start with Unit 1, which was polynomial and rational. Okay, we definitely need to know the formula for average rate of change. Okay, and then all of these facts about rates of change for AP Pre-Cal. What increasing means, decreasing, concave up, concave down. They have to do with the sign of the rate of change. And for concavity, really it's the sign of the rate of change of the rate of change, if you look at it. But you know, these are like fully suitable definitions for these concepts. We need to know that a linear function has a constant rate of change, and that the rates of change of a quadratic function form a linear pattern. Okay, we also need to know, kind of like later on when we go to do modeling, that a degree n polynomial has constant nth order rates of change when the x values are evenly spaced. Okay, and for a local, or also called a relative maximum, in pre-calculus we just say that's where a function goes from increasing to decreasing, and a minimum is where that function goes from decreasing to increasing. Okay. Now, the point of inflection, and this is a cause of a lot of confusion. Honestly, it's a cause of confusion in calculus as well, and I think it's better as a calculus topic than a pre-cal topic, so I understand. But what you need to know is that a point of inflection is where we change concavity. And what I might point out that I don't see on this formula sheet about concave up and concave down is that it's kind of like, it's like the attitude of the graph. Is it smiling? You know, a concave up graph can be smiling, whether it's increasing or decreasing. It's like kind of a mischievous smile, but it's still a smile. And that concave down is going to be where the graph is frowning. You know, we can be frowning while increasing or decreasing. So it's important to remember that the function, like whether it's increasing or decreasing itself, does not impact the concavity. It has to do with whether the rate of change is increasing or decreasing. Okay, but a point of inflection is where we're changing concavity. So it might be something that looks like that, you know, right there, if we're looking at a picture of the graph of the original function, but occasionally in AP Pre-Cal we're looking at a picture of the graph of the rate of change. Okay, so, and that's where I said the second line, that's where the rate of change switches from increasing to decreasing or decreasing to increasing. And because I think there was probably too much of the word change floating around here, I think, you know, would be easy to just change that word to switch. And then the rate of change of the rate of change changes signs. I think that's really more of a calculus characterization, but I wanted to throw that in there just for anybody that, you know, was going to need that. Okay, also in the realm of polynomial functions, if z equals a plus bi, and that's like an a complex number, and that's a root of a polynomial with real coefficients, then z bar, the complex conjugate, a minus bi, is also going to be a root of that polynomial, which is to say that for a polynomial with real coefficients, complex roots come in conjugate pairs. Okay, then we also need to know the definition of an even function and an odd function, and I'll just throw those out here. An even function has symmetry across the y-axis, and an odd function has symmetry across the origin. But those are the formulas that we would need to know about an even and an odd function. We need to know about the end behavior of a polynomial. We need to know that that depends on the degree and leading coefficient of that polynomial. And, you know, what I always say is just like kind of think about, is it even, odd, positive, negative? And if it's, say, even degree polynomial with a negative leading coefficient, just think about y equals negative x squared. It's going to have the same end behavior as that. That's a way that we can kind of like simplify it for ourselves to, you know, keep ourselves from making errors. But we do need to be familiar with that limit notation as well. But, you know, again, if you need like a lot of detail on any of these concepts, go back into my AP Pre-Calculus playlist and you'll see like all the lessons and you can get the actual details. This here, we're just writing down the formulas we need. All right, moving on to rational functions. Suppose we have r of x equals p of x over q of x. R is the rational function, p and q are polynomials. Okay, the domain of R is going to be the set of all x's for which q is not 0. Anytime where q is 0, that is an x value that will not be allowed to be in the domain of R because it causes division by 0. Okay, now if both p and q are equal to 0 at a given point, it's going to be more complicated, right? We might have a hole, we might have a vertical asymptote. But if q is equal to 0 and p is non-zero, then that's a guaranteed vertical asymptote, which is kind of what you can see at the bottom of the screen. If x equals c is a 0 of q and not of p, that's an automatic vertical asymptote. And then I think I did this, yesterday with some other people, and I was drawing some examples of like some limits they might ask us about, like things that must happen. If we've got a hole in the graph, that's when we've got an x value being a 0 of the numerator and the denominator. And if there's like multiple multiplicities on both, let's say the multiplicity in the numerator is greater than or equal to the multiplicity in the denominator, after canceling, there's no more factor in the denominator. If after canceling all of the things that can be canceled, that factor is still in the denominator, it's still going to be a vertical asymptote. But if it wasn't and it was still in the numerator, after some canceling, say we had 2 powers in the numerator and 1 in the denominator, it would be a hole in the graph. It's just that the y-coordinate of the hole would be 0. Okay, yeah, and then the one other thing that I see right there is that the zeros of the rational function. Those are zeros of the numerator that are not also zeros of the denominator. Now here we're talking about the end behavior of a rational function. And the people I was working with kind of wanted some more examples on this. But remember that for AP Precalculus, what we can do is we can just grab the lead term of the numerator and the lead term of the denominator, that's the highest degree term, divide them by each other, that's the work you see me doing off to the side in red, and then that will tell us the end behavior, right? So if we divide the two things, like the first r of x, we divide the leading terms and we get 2x, r of x is going to have the same end behavior as y equals 2x. And then, for the other ones, if the degree on the denominator exceeds the degree of the numerator, then it's going to be equivalent to something where the numerator is staying constant and the denominator is growing, which will mean that it has a horizontal asymptote of 0. And then if the degree is the same, we're dividing the leading coefficients, just like we did in Algebra 2. But if the degree of the numerator exceeds the degree of the denominator by exactly 1, then we'll have a slanted asymptote, and we're going to get the equation for that using polynomial long division. And you can see the actual details of that work right there. If you wanted to pause and copy it in, or pause and try to make sense of it yourself, you're welcome to. But if you need more detail than that, once again, I'm going to refer you back to the playlist and the various videos from throughout the year. Okay, I think kind of the last of the formulas we would need from Unit 1 is the binomial expansion idea. So I guess that's really just the triangle, but I think you're better off just understanding the concept of the triangle and everything than actually trying to memorize the triangle. I don't think that's the thing to do. No, it starts with a triangle of ones, and then we fill in by adding the numbers, kind of adding between. Okay, and then again, if you need more practice on this, go practice this, but just for binomial expansion, use Pascal triangle, or just gut it and multiply it out however many times. In an emergency AP exam, determining whether we get credit or not, we might want to, and we can't remember how to do the triangle, we're just going to try the best we can, right? Okay, and then the transforms. Okay, we need to know our dilations, translations, and reflections. And these are the relevant formulas we need. I don't want to spend too much time obsessing over these. We've done a lot of this work, and it seems like that's something that y'all were pretty solid on this year, at least the students in my class. Okay, Unit 2 is where we start to get into more of the formulas that we need to know, the exponential and logarithmic functions. So the first thing I wrote in blue, the most important thing about a log is really what it means to be a log in the first place. And I will re-emphasize that, and I'm sorry if you've been in my class for 2 years and heard me yelling at you about the fact that a log is an exponent for that long, but it really is that simple. Remember, a log is just a special exponent. So if the log with base b and argument a is just some number x, then x is the special exponent that I put on b to obtain a. And that's the whole purpose for a logarithm in the first place, is we know how to solve 2 to the x equals 8. We know we put in x equals 3. But 2 to the x equals 10 is not going to be as easy to solve. It's not a nice number. So we just call it the log with base 2 and argument 10. It's the special exponent I put on 2 to get 10. Now in red, underneath that, we've got kind of these fundamental identities that if we take a base and we raise it to a log with that same base, we're just going to get the argument back. And if we take the log with base b of b to the x, that's just going to give us x. If we really think about it in terms of like the special exponent thing, okay, that log on the red identity on the left, that log is the special exponent I put on b to get x. So if I put that special exponent on b, I should get x. And log base b of b to the x is asking the question, what exponent do I put on b to get b to the x? Well, of course I put x on b to get b to the x. It's that simple. Okay, now we need to know our exponent properties, which are kind of like these things right here. Actually, I don't know why I stopped there. It's really all of these are the exponent properties. And then we also need to know our log properties right there. We need our, product sum, quotient subtraction, product or power property for logs, change of base formula, and we need to know that natural log is log with base e, and if they don't put a base, that is implied to be base 10. Composition of functions and inverse functions are also part of Unit 2 in AP Precalculus. So I would just, point out that notationally speaking, this f of g of x is the same as that f of g of x. I personally really prefer the notation on the right, but you as a student, you need to be aware of and ready for both. Okay, and then if g is an inverse function for f, then we need to be able to compose them and just get x both ways. F inverse of f of x or f of f inverse of x, these need to both return me just x. All right, moving on to trig and polar. This is the type of thing where you would feel like there'd be a lot of formulas to write down, but we didn't find all that many when we were going through this yesterday. Okay, we need to really understand the idea of the standard position of an angle. And the idea of sine, cosine, tangent. But the work we did this year on trig, I've taught trig. It's only the second time I've taught precalculus, but I've taught trig in other classes before, and this was by far the best I've ever done on it, as far as student outcomes and like how I feel about how I presented the content. What we did was really good. We boiled everything down to 30, 60, 90, and 45, 45, 90 triangles, except for the extremes, which you can see on the unit circle labeled in red. And those were just basically easy enough that we didn't even have to think about them all that much. We were thinking about for sine, the vertical displacement from the x-axis, and for cosine, the horizontal displacement from the y-axis. I would point out that the arc length, the length of part of a circle, with angle theta radians, it's just the radius times theta, and that's an important formula that sometimes goes forgotten about, and sometimes it's supposed to be a really easy question in multiple choice, but I had a lot of people missing it because they forgot you're just supposed to multiply r times theta. Okay, we need to know the general shape of a 30, 60, 90 or 45, 45, 90 triangle, but man, as students in my class, I am not worried about y'all knowing that. Y'all are really, really solid on your unit circle trig, so I think I'm just going to move on to the trig identities. And this is something I feel a little less confident on for the students in my pre-calculus class. Okay, I know that a lot of us are super solid, like knowing all of them, knowing everything we're supposed to know, but I know that some of us are still not totally remembering. Okay, what I would say, these are the ones that we probably, I don't even know about the even odd identities, sine of negative theta and cosine of negative theta. I found them to be quite useful in proving other identities, but they're not explicitly mentioned, I don't think. Maybe they are, I don't recall. Actually, yeah, I do think I caught them just not in a place I would have expected. But we definitely need to know our reciprocal identities, which is these. Okay, we need to know our Pythagorean identity. I only know that one. Okay, I can generate the other two by dividing that equation by either sine squared theta or cosine squared theta, both sides, to give me each of the other two Pythagorean identities. We need to know our angle addition formulas. That's a must. Okay, that was a miss. That's a little better. We need to know our angle addition formula for cosine. And we need to know our double angle formulas. These are the ones I know. And then to generate the other two for cosine of 2x, I'm going to just substitute either on cosine squared x or sine squared x with a Pythagorean identity. Okay, I'm just going to say, because I remember these being mentioned in the course description, I'm going to put those under highlighter as ones we must absolutely know. And there you are. There's our trig identities for AP Precalculus. for graphing trig functions, this is another thing students in my class are very strong on this year. I would say for the graph of a standard sinusoidal function, a times the sine of b times x plus c, then add d, or, replace sine with cosine. A is going to give me the amplitude, or at least the absolute value of a is going to give me the amplitude. The period is something I can find using the formula 2 pi over b. The phase shift will be negative c, and I did write it as x plus c because that's the way they write it on free response question 3 in AP Pre-Cal, so just, remember that shifting right causes us to replace x with x minus a number. And then the midline is y equals d, that number that's added onto the outside. Okay, and so you can see my picture of like the standard positive sine, negative sine, positive cosine, and negative cosine graphs right there. And then we kind of just fit in all the pieces. But again, this is something y'all were really good at. As far as the graphs of tangent, cotangent, secant, and cosecant, we did them. You can go back and watch video of me doing these graphs and these example problems. But I think the best way to like determine which is which, or, determine what you're looking at in a multiple choice setting, which of course this would be a multiple choice setting because we know this is not part of the free response, is by the vertical asymptotes. Okay, remember that a vertical asymptote is caused by division by 0. Tangent is sine over cosine, so the vertical asymptotes of y equals tangent x are precisely the values of x that cause cosine to equal 0. That's pi over 2, 3 pi over 2, negative pi over 2, probably 5 pi over 2, values like that. And then for cotangent, secant, and cosecant, we can kind of go in and like go with the same lines of reasoning and figure out what's going on there. For inverse trig, okay, inverse trig is something that I just don't think we spent enough time on in my class this year. If I was going to teach AP Pre-Cal again next year, which I'm not, I would spend a little bit more time on inverse trig functions. I think, my perspective as an AP Calculus teacher may have kind of poisoned me against to be like, it's not all that important. It's more important that we have just like a general understanding of the unit circle, which was really useful when we went to do polar. But then, on free response question 4, I feel like sometimes I wish I'd have given you a little more experience on that. What I need you to know is notationally these things that I'm going to underline right here. I don't want to red highlighter it. I just want to underline here and here that arc and inverse notation that like is sine to the -1. That does not mean cosecant x. Okay, that's why I don't like that notation. I like to just call it arc sine. Arc sine of x is inverse sine. It's the arc whose sine is like root 3 over 2 or 1 or 0 or something. Like, look on the unit circle. Where is sine root 2 over 2? Well, that's probably the easiest place would be pi over 4. Now on the right, what you can see, I've already highlighted one of them, that these are the places where the arc trig functions take their values from. Remember, they are functions in their own right. So they need to only produce one value when I plug in an x. So for like, say, arc cosine of 0, where on the unit circle is cosine most obviously equal to 0? We need to return one value. You want to plug in arc cosine of 0 into your calculator and get one value returned. Okay, well that's just going to be pi over 2. First of all, because it's the most obvious, and second of all, it's from that section of the circle that I showed you. But that's why it's that section of the circle, is that was what somebody a long time ago decided was the most obvious place on the unit circle where these things were happening. Okay, in the world of polar, this was really easy if we did our job right and when we were studying trig. If we actually learned, unit circle trig, this was very easy. We just allowed for the idea of the radius being negative. Okay, because in AP Pre-Cal, fewer triangles, more like circles of various radii intersecting with terminal rays. We were doing this all over the place. We just had radius 6, radius 10. Okay, with polar, we just have to allow for the possibility that theta could be negative. So for the first one in red, 5 and pi over 3 are its distance from the origin. Theta is exactly what you expect it to be. Okay, it's from the unit circle. So pi over 3, we know where that is on the unit circle. It's a 60-degree reference angle. 5 units away from the origin. That's why I'm drawing you there. But then if r goes negative, okay, we just go backwards. So -2 along pi over 4, you see that dotted black line, that's theta equals pi over 4, what we would think of as theta equals pi over 4. But I'm going to go backwards 2 units into the third quadrant, and that's, that would be where that point is, -2 comma pi over 4 point in the polar coordinate system. Now, Formulas that we need to know about polar. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and theta equals arctangent of y over x, provided x is positive. If x is negative, we're probably going to have to add pi, or just like kind of think about it a little bit more. But we are always going to have to be like kind of careful with theta. And I think that's what I've got to say about polar. In my class, we did modeling at the very end of the year. And, you know, there weren't a lot of formulas for that. You need to know how to do a regression and all that stuff. That's not a formula. That's a skill that you needed to build through the year when we were studying and working so hard along the way. Okay, one thing I would just remind you, though, is if we're looking at a semi-log plot where the vertical axis is logarithmically scaled and the graph looks linear, we're actually looking at an exponential function. And for a residual plot, pattern means inappropriate and no pattern means appropriate. And that's what I've got to tell you about modeling. Now, I think, yeah, that's really all I have for the formulas. I recognize that because I am a relative novice in the pre-calculus game, I may have missed one or two. I lived off that course description, though, for the whole year, and so I like to think I'm pretty familiar with what we needed to know for the AP exam. Okay, I'm not even touching AP Pre-Cal Unit 4. That's not on the exam. These are formulas we need for the AP Pre-Cal exam. If I've missed any, put them down in the comments below, and maybe in the future I'll follow up with another video. But that's going to be all for this one. Thanks for watching.